Let's look at solving exponential and logarithmic equations, keeping in mind that they are inverses of each other. The inverse of the exponential is the log, and the inverse of the log is the exponential. So they'll play off of each other when we solve these equations. We'll look at exponential equations first, and we'll look at the first way of solving an exponential equation, and that is, seeing if we can make the bases match. If it's possible with an exponential equation to make the bases match on both sides, then we see that same thing coming into play where if the bases match, then they kind of cancel out and the exponents have to be equal. That's what this property right here is saying. If you have, I'll just write it over here, a b to the m power equal to a b to the n power. If those two quantities are equal to each other, then it must flow from that the two exponents must be equal to each other. M must be equal to n. So if the bases match, we can kind of do a canceling out thing and set the exponents equal to each other. So investigate your equations first to see if that is a possibility. And that can actually be used on these two right here. I have a 2 to the negative x equal to an 8. Well, there's a relationship here. 8 can be written as 2 to a power. 8 is the same thing as 2 to the third. If I can rewrite my equation where my bases match, then it falls from that the two exponents must be equal to each other. The negative x in the exponent position must be equal to the 3, which is a simple equation to solve. Solving it for x, we get x equal negative 3. It's the easiest type of exponential equation to solve. Same thing over here. I see that the 125 and the 5 have a relationship where the 5 is just 5 to the 3x minus 6, but 25 can be written as 5 cubed. If I can write it where the bases match, again, it must fall from that the two exponents would have to be equal to each other. The exponent 3x minus 6 equal to the exponent of 3 is a very simple equation to solve when we add 6 and then divide by 3. So x is equal to 3 in this case. So exponential equations, check to see if you can make the bases match. If you can't make the bases match, you can't solve it that way, then what we'll do is we will use the inverse of the exponential, which is the logarithm, to solve an exponential equation. But we first have to isolate the exponent term. Then what we'll do is we'll take the natural log of both sides and we'll simplify and solve for x. Let's look at this first one. 6 to the x equals 17. I can't think of a perfect power to write 17 as 6 to some perfect power. But I can use the natural logarithm to solve this. The logarithm is basically going to undo the exponent. Here is our exponent term. It's the term that has the exponent, the base and the exponent. It's isolated, it stands on one side, so simply take the log of both sides, and I'm going to choose the natural log. So I'll take the ln of 6 to the x equal ln 17. Now I said they're inverses of each other and they're going to undo each other, and you might not see that at this point, but remember a property that we discussed earlier. If you have the log of something raised to a power, then that power can drop right in front of the logarithm, leaving us with x ln 6 equal to ln 17. So by taking the log of the exponential, we see we can use that property that the exponent can drop in front of the log, and since the exponent was my variable, I can now solve for it. It's no longer in the exponent position, it comes down in front. So to solve this for x, I just have to divide both sides by ln 6. Ln 6 is just a number. And so it's like a coefficient on x. We can divide both sides by it and get an answer of ln 17 over ln 6. and that is what we call the exact answer using logarithms. If we want a decimal approximation, we'll use these little wiggly lines and go to our calculator and do ln 17 divided by ln 6. The decimal approximation would be 1.581. So this is the exact answer in terms of logs, logarithms or natural logs, and this is the approximate answer, the decimal approximation. So if we can't get our bases to match, we need to take the log of both sides. Let's take a look at this one. This is one of those where we'll have to take the log of both sides, obviously because I have it in this section. But let's look at our steps here where we need to isolate the exponent term. Over here, the 6x was the exponent term, and it was isolated. It stood alone. It's the base and the exponent that goes with it. Over here, the exponent term is the e to the 2x plus 1, not the 8. The 8 is multiplied by that. So this is the exponent term that has to be isolated. So we must isolate that first before we can do anything. So like with any equation, if I had 8x equal 24, I'd have to divide by 8 to get rid of that so I could work on solving for x. This is the same thing. I've got to divide by 8 to work on getting to the x that's in the exponent position. So let's start off with that division of 8. That goes away and I have an e to the 2x plus 1 equal to 3. That e is still there. I can't get rid of it. The only way I can get rid of this e, which is a base, is to take the log of both sides. So we're going to take ln of both sides. ln just works really nicely for this one. Because what's the understood base on ln? It's an understood e. And if I do an ln on both sides, I see that property where my bases are matching. That stuff cancels, and I'm left with a simple equation, 2x plus 1 equal ln 3. A simple equation to solve. So I isolate the exponent term, taking the log of both sides, and the ln is a perfect log because it matches, the bases match and they cancel. Now solving for x, we'll subtract 1 and divide by 2. So it'll be ln 3 separate from that minus 1 and then divide by 2. So the exact answer in terms of logarithms, in terms of the natural log, would look like this. If I went to my calculator, I could get a decimal approximation, ln 3 minus 1 over 2. So ln 3, close the parenthesis, minus 1, close the parenthesis for the numerator, divided by 2. ln 3 minus 1 divided by 2. 0.049. Exact answer, decimal approximation. Let's locate the exponential term here. It's the, let me close that parenthesis off right there. Okay. The exponential term is this 10 to the 5x. We've got to get that isolated by itself on one side, which means we need to remove this 4 and remove this 1. Since the 4 is multiplied, that's parentheses indicating multiplication, we'll go ahead and divide both sides by 4 to get things going. Okay, still working on isolating this 10 to the 5x. Let's go ahead and subtract 1. So I get 10 to the 5x equal 9/4 minus 1. Now we have to pull in a little arithmetic. This is like 9 over 4 minus 4 over 4, which is 5 over 4. Just pulling out that arithmetic. 10 to the 5x is equal to 5 over 4. Now that the exponent term is isolated, we were successful in getting that by itself. It's time to log both sides. Now notice I've been choosing LNs, and boy, this LN worked beautifully over here because the bases matched. How about we do for this one, instead of an LN, let's take log base 10 of both sides. Since the base there is already 10, oh gosh, I lost my page. There we go. Since the base is 10, log base 10 is just going to help us that much more. Log base 10 of 10 to the 5x. Now notice I normally don't write the base on the base 10 on log base 10, but I'm just putting it in here for emphasis. See, the base is matching. That stuff's going to cancel. Gives us a quick follow through. 5x equal log of 5/4. And then we need to take that and get rid of this 5. Now here, I guess I could say divide both sides by 5, but I am more partial to say and multiply both sides by 1/5. You just get a cleaner looking answer if you do that. 1/5 log of 5/4. That's the exact value in terms of a common logarithm. Let's go to the calculator and get an approximate value. 1/5 log of 5/4. Okay, so let's type that in. 1 divided by 5 log of 5 divided by 4. 0.019. So using the natural log to solve those exponential equations gives us these results.